Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 5, Refraction at a Plane Surface. And we're not refracting light on the surface of a Boeing 737. We are refracting light at a flat surface. Now, every transparent material has what's called an index of refraction. We use the letter N for the index of refraction. And it's a measure of optical density. And you can think of optical density as the ability of a material to slow down light. Now, we learned in Unit 1 that the speed of light is 3 times 10 to the 8th meters per second. And that's the speed in a vacuum or also in air. It might slow down a little bit in air, but it's not a significant difference. So we say air has an index of refraction equal to 1. Water has an index of refraction equal to 4/3 or 1.333. And certain types of glass have an index of 1.5 or 1.5. So light travels slower in glass than it does in water, than it does in air. Now we're going to draw our normal horizontally, and the vertical line separates two media. The medium on the left has an index N, and the medium on the right, the second medium, has an index of N prime. Remember, the normal is a line that's drawn perpendicular to a surface. Now, for the purposes of this example, we'll say that N prime is greater than N. We'll send in a light ray at the normal. And what happens is the light ray is bent toward the normal if light is traveling from a lower index of refraction to a higher index of refraction. Alpha is called the angle of incidence, and it's the angle between the incoming ray and the normal. And alpha prime is called the angle of refraction, which is the angle between the refracted ray and the normal. Now let's draw the other option, which is where light travels from a higher index to a lower index material. So now in this case, N prime is less than N. Our incoming ray, and this time our refracted ray is bent away from the normal. So there's something called the law of refraction. It was found by a gentleman named Snell, who was a very modest fellow and named it after himself. Snell's law says N sine alpha equals N prime sine alpha prime. Now, let's say you're looking down at the bottom of a swimming pool, pretty close to where you're standing. Light from that place is bent away from the normal, and the swimming pool appears to be shallower than it really is if you extend that ray that's coming into your eyes back. That's the apparent depth. Now, let's say you look further down the pool, further away from you at a place at the bottom of the pool. Now, the angle of incidence is greater than the previous angle of incidence, and therefore the angle of refraction is also greater. And when you extend that refracted ray back, the pool seems to be even shallower. So Snell's law tells us that as the angle of refraction increases, the angle of incidence increases, and vice versa. Alpha 1 and alpha 1 prime are the angles when you're standing close to where you're looking, and alpha 2 and alpha 2 prime are the angles where you are looking further away. Alpha 2 is greater than alpha 1, therefore alpha 2 prime is greater than alpha 1 prime, and the pool appears shallower as you look further down the pool. Now let's further examine light that travels from a higher index to a lower index. So n is greater than n prime. So let's make this line straighter. There we go. So we're sending in this blue ray of light that's bent away from the normal, and let's say it is refracted in that direction. Now let's send another ray of light, we'll make it red, at a higher incidence, angle of incidence, and it is bent even more away from the normal. And now let's send in this green ray of light, and that green ray of light, its refracted ray goes right along the surface, the interface between these two media. That angle that's made, that angle of incidence of the ray, that is the last ray that's refracted, is called the critical angle. We use capital letter A to denote the critical angle, and it is the angle of, it's the largest angle that a ray, an incident ray, can be refracted. And the formula to figure out A is sine A equals n prime over n. Now, what do you think happens when you send in a ray greater than the critical angle? What's going to happen is those rays will be reflected at that interface. And the laws of reflection that we learned in Unit 3 and Unit 4 are obeyed. So the angle of incidence equals the angle of reflection. So this purple ray is hitting the interface at an angle greater than the critical angle, and it is reflected. Now, this critical angle explains a couple of phenomena. One phenomenon, you may have had the experience of driving on a highway on a hot day, and you see a wet spot on the road far down the road. And when you get there, it's not wet. It disappears. Why is that? Well, the road on a hot day has a hot layer of air directly above it and a slightly cooler layer of air above that. The hot air has a lower density and a lower optical density and a lower index of refraction than the less hot air above it. So let's send a ray of light from the sky to this normal that I drew, and we'll send it at the critical angle, so it will be refracted along the interface. Critical angle A. Now let's send a ray at greater than the critical angle, and as we just learned, that ray will be reflected. And so when you're driving, what you're seeing is not a wet spot. You're seeing a reflection of the sky in the road. As you're driving down the road, you see this wet spot far down the road. As you pass this point here, you're past the reflected ray, and the so-called wet spot disappears. This is the explanation of mirages in the desert. Okay, you can get these same layers of hot air and less hot air over the sand in the desert, just like you can get them on a hot road. Now, the other thing that the critical angle explains is fiber optic cables. Why does the light stay inside this clear cable? Why doesn't it leak out? So, the fiber optic cable, let's say, has an index of N. It's surrounded by another transparent material called the clad with a different index of refraction. Let's say the clad has an index of N prime. And N, the index of the fiber, is greater than the index of the clad. So we'll draw our normal. And we'll send in a light ray at greater than the critical angle. What's going to happen? Alpha is greater than A, therefore we're going to get a reflection inside the cable, which is going to strike the opposite side of the cable, also at that angle alpha, greater than the critical angle, and that will be reflected. And that's going to hit the opposite side and be reflected again. So the reason why fiber optic cables are able to keep the light inside of them is there's total internal reflection because the angle that the incident ray hits the inside of the cable at is greater than the critical angle. Now for paraxial rays, remember these are rays that are close to the optical axis. Therefore, alpha and alpha prime are really, really small. There's a simplified formula you can use to determine the object and image distances. And the formula is u prime over u equals n prime over n. So let's explain what these variables mean. A is where the interface crosses the optical axis. M prime is the image location. M is the object location. So U is defined as a distance from A to M. It's the object distance. In this case, it goes from right to left. Therefore, it's a negative number. And U prime equals AM prime. It's the image distance, also going from right to left, also a negative number. N is the index of refraction of the medium on the left. Remember, we send light in from left to right, so it's the first medium that the light passes through. And N prime is the index of refraction of the second medium, the medium on the right. Now, for a medium that's surrounded by air, it's going to appear to be less deep or less thick than it really is. And there's a simplified formula we can use to calculate its apparent thickness. So it's got an actual thickness of D, it's got an index of N, surrounded by air. And we're going to be looking at it along the optical axis. So its apparent thickness is equal to D divided by N. So why does light bend when it goes from one medium to another? Well, let's think of this cardboard here as a
bundle of light rays, a beam of light rays that are all going in the same direction, and they're traveling in a medium where the index of refraction stays the same. So the beam just goes straight through. So my quartz counter isn't completely frictionless, but you get the idea. Now, let's see what happens when our light bundle goes from a smooth surface to a rough surface, which mimics going through a medium of low index of refraction into a medium of high index refraction. In both cases, this area is going to slow down the light beam or the light bundle. And we'll send our light beam in at an angle. And let's see what happens. You see how the light beam bends toward the normal. We'll do it again. So this edge of the light beam is hitting the higher index that slows it down first, and it causes the light beam to bend toward the normal. So let's think of this cardboard tube as a light beam. Okay, all the rays are going in that direction. And we'll send it from, let's say, air to glass. So the right side of the light beam will encounter the glass first, and it will slow down and cause the light beam to bend toward the normal. Okay, now I suggest that you watch Unit 5P. That is the unit where I will be going over word problems. I'll be plugging into the formulas that I gave you in Unit 5.